Hello, hi. Uh, Welcome to this video about the approaches of how to attain optimal model complexity. I, Rajab Solimo, the looking at model complexity, we say this refers to the complexity of the function attempted to be learned, similar to a polynomial degree. The nature of the training data generally determines the proper level of model complexity. Model complexity and overfitting are two of the main problems that can occur in machine learning. Model complexity can lead to model that is too complex and does not generalize well to new data, while overfitting can cause the model to perform well on the training data but poorly on new data. Therefore, there are several ways to prevent these problems, which include using simpler models, using regularization techniques, splitting the data into training set and a test set, stopping and cross validation. It's important to monitor the performance of the model as it is being trained and adjust the parameters accordingly. ML model complexity is measured by the number of parameters that model possesses. A model is said to become more complex if the more parameters are added, and conversely, if some parameters are removed, model will become simpler, that is less complex. It does not imply a one-to-one relationship between the model complexity and the number of parameters, since each parameter is not necessarily equal important. So why do we care about this model complexity? A model should not be too simple, because then it would not be capable of capturing the process behavior with reasonable degree of accuracy. On the other hand, a model should not be too complex, because then it would possess too many parameters to be estimated with the available finite data set. Thus, it is clear that somewhere in between there must exist something like an optimal model complexity. Of course, the optimal model complexity depends on the available data, the specific and etc. What are some of the approaches that we're looking at to attaining the optimal model complexity? We're looking at regularization here, which is a set of techniques that reduce model complexity, usually by adding regularization terms to the fitting error function, which grow with some model metric. A basic example of this regularization is L1 or L2 regularization. L1 regularization, for example, increases error linearly with the sum of model weights. For a linear regression fitted using the residual sum of the squares algorithm, the error function would be the following. Which is in this equation. Regularization allows the optimization process the possibility of using a more complex model, but complexity also helps reduce the error. But at some point, it forces the optimization to settle for a reasonable simple model. When additional complexity doesn't reduce the error, regularization leads to worse fit on training data, and when set correctly, to better fit on out of sample data, and therefore better generalization ability of the model. Looking at using simpler models, this may seem counterintuitive, but simpler models are often more robust and generalize better to new data. One way to create simpler models is by avoiding too many features. If a model has too many features, it may start to overfit the data. It is important to always select only the most relevant features for the model. Split the data into a training set or a test set, which will allow the model to be trained on one set of the data and then tested on another. This can help prevent overfitting by ensuring that the model generalizes well to new data. Using alert stopping. Alert stopping is another technique that can be used to prevent overfitting. It involves training the model until the validation error starts to increase, and then stopping the training process. This ensures that the model does not continue to fit the training data after it has started to overfit. We have the cross validation, or as an approach of attaining minimal model complexity. Cross validation is a technique that can be used to reduce overfitting by splitting the data into multiple sets and training on each set in turn. This allows the model to be trained on different data and prevents it from being overfitted to a particular set of data. What are some of the methods used during or for cross validation? We have what we call the validation set approach. Here we divide our input data set into training set and test of validation set. In the validation set approach, both the subsets are given a 50% of the data set. The second is leave P out cross validation. In this approach, the P data sets are left out of the training data. It means if there are total n data points in the original input data set, then n minus p data points will be used as the training data set and the p data points as the validation set. This complete process is repeated for all the samples, and the average error is calculated to know that the effectiveness of the model. The third one is leave one out cross validation. This method is similar to the leave p out cross validation, but instead of p, we need to take one data set out of training. It means in this approach, for each learning set, only one data point is reserved, and the remaining data set is used to train the model. This process repeats for each data point. Hence, for n samples, we get n different training set and n test sets. We also have the K4 cross validation. K4 cross validation approach divides the input data set into K groups. Of samples of equal sizes. These samples are called false. For each learning set, the prediction function uses a K1 function false, and the rest of the false are used for the test set. This approach is a very popular cross-validation approach because it is easy to understand and the output is less biased than other methods. The fifth is stratified K4 cross-validation. This technique is also similar to the K4 cross-validation with some little changes. This approach works on stratification concept. It is a process of rearranging the data to ensure that each default or group is a good representative of the complete data set. To deal with the bias and variance, it is one of the best approaches. The last is holdout method. This method is the simplest cross-validation technique among all. In this method, we need to remove a subset of the training data and use it to get prediction results by training it on the rest part of the. Another approach is to monitor the performance of the model as it is trained and adjust the parameters accordingly. The most straightforward way to monitor your ML model is to constantly evaluate your performance on real-world data. You can customize triggers to notify you of significant changes in metrics such as accuracy, precision, or the F1. Here are the supporting references to this work. I thank you for your time.